Good morning and welcome to the third lecture in our series this year. We were really happy to have you on this kind of grim looking day. I am Stephanie Marcus and I'm representing the Science, Technology and Business Division here at the library. I'm going to keep this short because the speaker is condensing his talk. He has so much to say and we want to hear as much as we can. Scott Braun is a research meteorologist at NASA Goddard. He earned his PhD in atmospheric sciences at the University of Washington. And after that, he did a postdoc at the National Center for Atmospheric Research in Boulder, Colorado. Not a bad place to be. And he was there for a number of years before coming to Goddard, and he's been there ever since. But this year, a very exciting event, Dr. Braun was elected as a fellow of the American I can't say that word. You know, the American Weatherman Association, the American Meteorological, I hate that, Society. Everybody say it with me. And he is a fellow, and you really have to have a long record of research and be a really outstanding person. So I think we should all congratulate him and welcome him back to the library.
All right, well, good morning, everybody. Thanks for coming out. So I intended this talk to be for a general audience. It's loaded up with a lot of animations. In fact, the file size, for those of you who have worked with PowerPoint, you're probably used to maybe a few megabytes file size. I'm really close to 2 gigabytes on this one. So it's packed with animations. I find that just works really well. So we're going to talk a little bit about hurricane hunting. You may have heard about hurricane hunting in the past. Let's see if I can get this to advance. There we go. So what is hurricane hunting? So this is basically using aircraft to go out and take measurements in storms for two different reasons. One is to just get data to monitor the storm. So what's its current location and what's its intensity? That information is critical for just understanding the evolution of the storm. It's also used for the long-term data record that goes back to the 1800s or so. It's a way for us to kind of track how things change over time. The data is also used in some circumstances to collect information that can go into the computer forecast models to improve those models. So a model is only as good as the information that goes in. You may have heard garbage in, garbage out. Well, that's true for models. And a lot of models don't have much information on the storm structure. And so by flying aircraft into these storms, you can get that structural information, feed it into the models, and it can improve the forecast. So that's why it's done. I'm going to give you a little bit of the context of why we might do it too. So imagine yourself a forecaster at the National Hurricane Center. You're faced with Tropical Storm Harvey out in the Atlantic. We're looking at two different times here, but just look at the one on the left at the moment. This is Harvey early on in its life cycle. The forecast calls for it to go over the Yucatan Peninsula and into the Southern Gulf. They expected it to be a tropical storm all that way, and then beyond that, it was hard to say what was going to happen. Now, if it goes along that path, it may just continue westward and hit Mexico as a minimal storm, and all the better there. Nobody really gets hurt. However, sometimes with these computer models, you see that they always kind of, over time, they're leaning to one side. It's like every forecast cycle, they want to go more and more to the right or more to the left. And my guess is in this case, that's what happened, because if you look at the plot on the right, that is after Harvey has come into the Gulf of Mexico. It's still a tropical storm. It's a bit more to the north and to the right of the original track. So now as a forecaster, you're faced with the question of, well, where is it going to go? They kind of think it's going to go up to Texas here, but that's a broad coast. And if you're off, how much of that coast are you going to evacuate? Depends on the storm intensity. If it's a tropical storm, people aren't going to leave. If it's a category 4 or 5 storm, people are going to get away from the coast. And at this particular time, they were forecasting the storm to make landfall as a tropical storm or minimal hurricane. So at that point, you probably wouldn't do much if you were living on the coast. Of course, many of you might remember that Harvey, shortly after this time, fairly rapidly intensified into a Category 4 storm by the time it made landfall. So this is a really difficult forecast problem, and as a forecaster, your decisions and your forecasts affect millions of people. it also can lead to costs of millions of dollars, whether you evacuate the right part of the coast or the more coast you evacuate, basically the more expensive it is. So these are really important decisions. So you want to make sure you're getting it right. You want to be getting the forecast right. And this is why you want to be able to collect information within these hurricanes. So the way that the operational centers do this right now, and this is primarily NOAA who does the operational forecasting, but the Department of Defense does their own forecasting as well. So they send out their own planes. So NOAA has the P-3 Orion aircraft. It's an old submarine hunter, basically, and it's got measurements that it takes as it's just flying along. They'll drop what's called a dropsonde that takes detailed vertical profile information. They have some radars on there that can give a sense of the three-dimensional structure of the storm, and that data is very useful for getting into the forecast models. They're finally getting to a point with these models where they're capable of ingesting that much data. Now, in the lower right there is the Air Force C-130 aircraft. They will do at least 2 flights a day into a storm when they get close enough to the coast. The amount of data they're collecting is pretty minimal. They're primarily just going out there to find the center and the intensity, so they don't have the radar and other things like that. But this makes up what you would call the routine hurricane hunting. But NASA gets into the game now and then in a couple different ways. And so what I'm going to describe in this talk is about how we do hurricane hunting, in a sense. But we'll start off talking a little bit about hurricane basics. Some of the things that, the reason we look at these storms is more from a research standpoint. We're not an operational agency, so we want to know, what's the structure of these storms, what makes a storm form, what makes it intensify. And we use observations from the vantage point of space, because that's NASA's core mission. But we also do things with aircraft, although only occasionally. And then we'll kind of sum things up at the end here. So for understanding a lot of what I'm going to show here, there's certain basics you need to understand about hurricanes, their structure, and how they work. So I'm sure you'll all recognize these equations here. These, oh, okay, maybe not. Maybe you'll recognize this structure. This is sort of an idealized view of a hurricane, just very circular. Doesn't assume there's any variation in structure around the center of the storm. So you get the eye of the storm in here, the eye wall, these deep thunderstorm or convective clouds that form the eye wall. The primary circulation is this in the northern hemisphere, counterclockwise rotating flow. In the southern hemisphere, it would be anticyclonic. We refer to it basically as cyclonic because it's in the same sense of the rotation of the Earth. And that will flip as you go from the northern to the southern hemisphere. So the primary circulation is basically the big vortex associated with the hurricane with the strongest winds within the eye wall. Now, in addition to that, we have what we call a secondary circulation, which is inflow at low levels in toward the eye. It rises up within the eye wall, and then it spreads out in the upper part of the storm. Now, when it first rises near the eye wall, it's still rotating cyclonically, or again, counterclockwise in the northern hemisphere. But then as it spreads out, it starts to change the flow direction. It starts moving clockwise. And you'll see that in some of the satellite imagery that I'll show later. So those are the basic structures of what makes a mature hurricane. But there's really a couple key questions that we as scientists still want to know. These are, I think, our top priorities in research, and that's how do storms form and what causes rapid changes in intensity. And there we're really talking about these storms like Harvey that go from a tropical storm to a major hurricane within the time span of just a day or so. Those are the ones that present the biggest forecast problem, because especially if this is occurring right off the coast and that rapid intensification is unexpected, people may go to bed thinking they're going to face a Category 1 storm in the morning and wake up to a much more intense case. That was true of Hurricane Charlie back in 2004 when it made landfall on the west coast of Florida. They thought they were getting a Category 1, and they ended up with a strong Category 3 or weak Category 4, I believe, in that case. So how do hurricanes form? Well, there's certain key ingredients you need for storm formation. First and foremost, you need warm ocean temperatures. The ocean temperatures have to be about 26 degrees Celsius or so, and that's around 80 degrees Fahrenheit. And you're primarily going to find that down in the tropics. So when you look at the formation zones indicated by orange, that's where you've got the warmest waters. You need high humidity because that favors cloud growth. If you have dry air getting into storms, that tends to evaporate the cloud droplets and rain droplets, and it also cools the air, which removes some of the energy that the hurricanes would otherwise work with to intensify. You need weak vertical wind shear, and that's the change of winds with height, and I'll illustrate it in the next slide. But basically, you need favorable large-scale winds that won't kill off the storm. You need background rotation. That often comes from just the rotation of the Earth. If you think about it, if I'm the Earth and this is a storm on the top of the Earth at the North Pole, if I'm rotating around, obviously my hand is turning. If I'm at the equator and I'm rotating around, it's not rotating. So there's no rotation from the Earth at the equator, even though it's obviously spinning real quick, but the rotation is sort of perpendicular to the axis of the storm. And so that's why we never really see storms form right along the equator. They're always off the equator. There are other types of disturbances that can create that background rotation. Some of these are very large scale. In the West Pacific, it's called the West Pacific Monsoon Gyre. It's just a very large area of low pressure that basically provides some weak rotation on top of the Earth's rotation. In the Atlantic, we have what's called African easterly waves. These are disturbances that come off of the west coast of Africa. They form about 60 to 70% of Atlantic hurricanes, and they provide rotation on a somewhat smaller scale than that West Pacific monsoon gyre. And they're often associated with thunderstorm activity, and it's those thunderstorms that provide the last element here, an initiating convective system. So you got rotation on the large scale, but you really want that rotation, if you want a hurricane to form, on very small scale. So you need some mechanism to concentrate it, and that's usually done by thunderstorm activity. So while we know a lot of these ingredients, we don't always know how they come together to form a storm, and it can be different from storm to storm. That's what's so complex about it. And it can be very sensitive to small variations in some of these ingredients. So it's a very difficult forecast problem. Now, once you have so coming back to this effect of vertical wind shear, this is a critical aspect of it because it really is a key determinant of whether or not a storm forms. So if you think of the winds as a function of height from the surface to the upper atmosphere, wind shear just means that the winds are changing with height. It may be due to a change in wind speed with height, or it could be a change in wind direction with the speed staying the same, but it's changing, say, from westerly at low levels to easterly aloft. Now, if you have this sort of represents the circulation in a hurricane, that cyclonic circulation down low, anticyclonic aloft, and if these are just being moved by the wind, obviously the one at upper levels is going to move faster than the one at low levels, so you get this tilting of the storm. And what that looks like in satellite imagery is this. So here's, I don't know the name of this particular storm, but this is the low-level storm center. The shear has exposed the low-level clouds, but all the deep clouds now have been pushed way off to the east. And within this is where you typically find this upper circulation. So when we see a storm go from when you can't see the low-level circulation to where suddenly it gets exposed, usually we know there's a strong wind shear, and that's often going to kill off these storms. Now, if the shear weakens again, then it might reform. Now, the other big question is what drives rapid intensity change? A couple plots here just to kind of illustrate this. This is just showing time along this axis, and this is wind speed in knots and surface pressure in the middle of the storm along this axis. And this is for Hurricane Wilma back in 2005, which up until recently, until Patricia, I think in the Pacific a couple years ago, and Maria may have equaled it, it was one of the more rapid intensifiers we had. It intensified about 95 knots in 24 hours. That's a huge increase. Normally we consider rapid intensity changes 30 knots in 24 hours. So this was pretty exceptional. And you can see I've got the strength categories listed here. So at this point it's a tropical storm, and by the end of 24 hours is pretty much right at category 5 intensity in 24 hours. So that's pretty extreme. The pressure drop you can see is rather precipitous here. This is about a 10% drop in the weight of the atmosphere above you. That's the equivalent of, say, climbing about a kilometer to a kilometer and a half up. As the air gets thinner, and it's not that thin at a kilometer and a half, but that's what it amounts to. This is very rare to see it this low at the surface. So now I'm going to play a little animation here that shows Hurricane Wilma down here in the Caribbean. The warm colors here represent the temperature of the ocean, and this entire region is above that 26 degrees Celsius, and in fact most of this area in the Caribbean typically gets to about 29, 30 degrees, maybe a little bit more at times. So there's plenty of fuel for the storm. You'll see an eye form here, and then at some point as it approaches the Yucatan, you get this massive eye form. And you'll also see in the wake of the storm this cooling. This is actual cooling that's induced by the storm because this warm layer is relatively shallow and the strong winds mix up deeper, colder waters to cool off the ocean. So I'm going to take a poll here. We're going to watch this one more time. I'm going to ask you to raise your hand when you think that this period of rapid intensification is beginning. So watch this loop, and when you think we've reached this point where the pressure is dropping rapidly, just raise your hand and we'll get a sense of when you think it's occurring. All right. Well, so most of you raised your hands when you got that awe-inspiring large eye forming. In reality, the rapid intensification occurs right about this time here when that pinhole eye occurs. That's often when we see rapid intensification, when you quickly get one of these small eyes forming. And then what happens when it developed that bigger eye was that you end up, if you go back to that schematic I had, where there were sometimes multiple bands of clouds around the center, sometimes one of those at a larger radius from the center will form what we call a secondary eye wall. That chokes off the inflow to the primary eye wall and weakens it and then forms a new eye, but it often forms one that's much larger. And that's what was happening when that large eye formed there. So now to get back to this topic of hurricane hunting. From a NASA perspective, our main goal is to try to do this from the vantage point of space. And there's a number of different things that we can measure from space. There's clouds and rainfall so that we can see the storm structure. There's the sea surface temperature that tells us about the energy available to the storm, the moisture that goes with the clouds, obviously, air temperature, winds, which are critically important, and even lightning information now. I'm not going to hit upon all these, but I'm going to focus on some of these, give you examples of what this looks like and how this relates to the intensification of a storm like Harvey. So a couple images here. This one on the left is one of the first images from space of a hurricane, Hurricane Hannah, from the TIROS 3 satellite. I think this is probably from the early 1970s. Now, if you didn't know that was a hurricane, you probably would just think, okay, it's just a big cloud system, but I don't really know what it is. It's really grainy. You probably didn't get very many of these images over the course of the day. Compare that to what we can do now, and with the lights in here, it's a little hard to see, but now with the latest generation of geosynchronous data, geosynchronous means that the satellite basically rotates with the Earth, so it's always looking at the same point on the Earth. And it allows us this type of data. And the latest series launched back in 2016 is called the GOES-R series, has twice the horizontal resolution as the previous generation, about 3 times the number of channels, which each channel allows us to see different aspects of these systems. And it has about 4 to 5 times the sampling in time. So where before we could see the whole globe in maybe every 2 hours or so, now we do it every 15 minutes. Where we used to focus in on a small area of the storm every 5 minutes, now we can do it as fine as every 30 seconds. And so this is zoomed out so you can't see the detailed structure, but it's showing Hurricane Harvey, that you can get a sense of the rotation in here. And if you look at some of these outer clouds, you can see this rotation that's sort of in the clockwise direction. That's that outflow aloft. And it's hard to see with the lighting here, but we can get near true color imagery now due to the combination of channels that they have on the sensor. So it's a very powerful sensor. And if you remember that introductory slide showing Hurricane Michael as it was making landfall on Florida, that's that super zoomed in view where you can zoom in really far and it still doesn't look pixelated. So that's how good this data has gotten. Now, there are times when you're looking at the clouds and all you see with the geosynchronous data is the clouds. It's hard to see what's beneath the clouds. In the case of Harvey, you might be able to guess as to where the eye is. There's a shadow in here because there's a deep thunderstorm there. And so, is that where the eye is forming? There are a lot of cases where all you see is a smooth cloud and you have no idea where the eye might form. And the forecasters have to come up with some estimate of the location of the center. So the best way that we have for actually identifying where that center is with what we call microwave sensors. So the atmosphere emits radiation at various frequencies. In the visible wavelength, you get to see it. So an image like this, you get to see it. They also do it in the infrared, which allows us to see the clouds at night. But even farther along the spectrum is microwave energy. And it turns out that when you have a lot of cloud water or precipitation, that emits a lot of energy in the microwave spectrum. So if you have an instrument that's sensitive to microwaves in that wavelength, you can actually detect where that precipitation is. And that's in fact what we have with a lot of different satellites. So this is showing information from a precipitation measuring satellite. There's a lot of different variations of these microwave sensors out there, but it's basically like getting an X-ray of the storm. So you can see this little donut shape here is the eye wall. So the sun is right in the middle of that. You get these spiral rain bands off of that, and you can, a lot of the times when you look at the total cloud cover, only a small fraction of that may actually have precipitation. And if we go back here, it's a little hard to see the deep convection there, but that's also where we see the red color here. That's just indicating that's where the heaviest rainfall is. So it's not always uniform around the center. Often it's what we call asymmetric. It's just on one side of the storm or heavier on one side of the storm. Now these types of measurements that give us this X-ray view of the storm is from a measurement that we call passive. It just means that the instrument is just looking at what's coming to it, but it's not doing anything else. Radar, if you've heard of weather radars, they're active instruments. So they send out a signal, that signal bounces off the raindrops and ice particles in the storm, and that energy bounces back to a detector, and it allows you to see different levels at which that information, energy is being bounced back. And so it allows us to see the three-dimensional structure of storms. We have a lot of these radars on the ground, but we also have one in space on a mission called the Global Precipitation Measurement mission. I'm actually the project scientist for this one now. And what you're seeing is that radar data in 3 dimensions as it kind of scans back and forth across it. This is that microwave data showing the 2D X-ray view. So the eye is right here and there's heavy rainfall around. You can see these warmer colors and then the blues aloft. This is all rain down here, but because the temperature decreases as you go up, you eventually get to a level where you reach the freezing point and everything above that is basically ice. In this animation now, it's going to sort of pull back the colors to where you can see the most intense rainfall in the eye and some of these bands, and then it restores it. So here's the eye wall. There's actually what's called a moat region there where there's not a lot of precipitation, and then there was actually a ring of precipitation around. This is sort of like with Wilma, that outer ring is that secondary eye wall. And so the radar data and these microwave sensors allow us to see that quite readily. And that tells forecasters something about how the storm might intensify. So if we see all the rainfall just on one side of the storm, that's usually an indication that it's affected by strong wind shear. If we see one of these rings form, then we know that the storm's likely to weaken a bit, but then after that, it could possibly re-strengthen and undergo a variety of cycles. They're called eye wall replacement cycles. Now the GPM satellite is probably the most accurate of the satellites out there. It's the only one with a radar right now, but it's part of a constellation of about 11 different satellites that can measure rainfall. But because it's the most accurate, we use it to intercalibrate all the measurements, try to make them all look as good as the GPM satellite, and that allows us to combine those measurements to start generating rainfall maps. And using certain visualization techniques, and you can get these nice smooth animations showing the evolution of rainfall about every half hour at about a 10-kilometer resolution. And these rainfall maps are really useful. In fact, for this mission, this product is by far the most used product, and it's very heavily used in a variety of applications that I'll talk about toward the end. But it gives us a way to kind of track some of these storms. And in a case like Harvey, for some reason this animation always sort of starts in the middle, but it'll restart in a moment. So what you're looking at here is accumulated rainfall. So it's the rainfall always adding up over time as the storm starts to come up from the south. It's reaching maximum intensity about this time, and it's got a lot of rain bands out to the east. So you'll start to see precipitation accumulating very rapidly out here in the Houston area. So the storm center was over here. It's moving very slowly, but all the rain bands were just feeding right into Houston. And for the time period of this animation, it got up to about 20 to 30 inches of rain. But there were, by the end of the storm, there were some areas that had 5 feet of rain, 60 inches from the storm, simply because of that very slow movement and the fact that all these rain bands were basically just training in to Houston. Every single one of them was hitting Houston, and that's why it was the disaster that it was. So now let's move on to the ocean temperatures here. This is a very long animation of the 2005 season. Many of you are probably familiar with this season. Generated such favorite storms as Katrina and Rita, among others. Now this is early in the season. This is June. You can see the warm waters here in the Caribbean and the Gulf of Mexico. So you'll see early in the season, that's where most of your storms form, because out here you still have a lot of cold water. So these disturbances coming from Africa have a much harder time developing until they kind of hit this warmer water. In fact, Dennis is, let's see, there's Brett. I think there's another one coming. I'll try to get up at least through Charlie here. Oh, there's Cindy. Here's Dennis. So it formed a little bit further out in the Caribbean, became a Category 4 storm. Emily became a major storm that hit Jamaica. It's about a minimum Category 5 before weakening at this point. So these storms have lots of energy down here in the Caribbean, where this warm water is very deep. It's several hundred meters deep. Whereas if you go up here to the fringe where Franklin is and it's causing this cooling, the water may only be tens of meters deep. So it doesn't take as much wind speed to mix up those colder waters compared to deep down in the tropics. So here's Irene. Irene kind of struggles most of the time. Maybe the thunderstorms get a bit more active while it's over the warmer water. But now look at this disturbance. It looks kind of uninteresting. It's just kind of spurting every now and then. But eventually it's going to get to this really warm water off the east coast of Florida, and there's Katrina. And then as it gets out over the Gulf, it rapidly intensifies into a Category 5 storm. You can see now it's strong enough to generate that cooling even where the water's fairly deep. And then a little bit later on, you start seeing all these storms. Ophelia, because it sits there, will generate a lot of cooling in that area. And Rita will eventually come in and do something very similar to Katrina. So this interaction with the ocean is important. One, the ocean provides the energy to the storm, but the storm may actually in some ways have the seeds of its own destruction in it, that if it cools those waters, and especially if it's moving very slowly, it really generates a lot of cooling. It's removing its own energy source because it's lowering the temperature of the water. So that's a pretty significant interaction that can occur, and it's actually can be fairly hard to forecast. So just going back to Harvey, this is the sea surface temperatures at the time of Harvey, and it's shown in the form of an anomaly, or the difference from the long-term climatology, or the difference from the average. So everything that you see in red means it's warmer than normal. Blue means colder than normal. And I hate to say it, but this pattern of almost all red is pretty typical nowadays. Due to global warming, we see more and more where much of the Atlantic and most of the globe is warmer than the long-term mean. And if you look here within the Gulf, the temperatures in the southern Gulf, not exceptional, they're just a little bit warmer than normal. But right along the coast here, the temperatures are up to anywhere from 1 to 3 or 4 degrees warmer than normal. And that certainly contributed to the rapid intensification of Harvey, especially leading up to landfall. So that's why having this information is critical. And it comes from sensors like the geostationary sensors that measure the infrared temperature. The only problem with that is it can't see through the cloud. So you don't know what's going on underneath the cloud and whether the storm is generating that colder water. But with these microwave sensors, we can actually see through the clouds. Just can't see maybe through the heaviest precipitation. So we can actually see that cooling occurring within the microwave data rather than what we get from the geosynchronous satellites. Now going back to moisture. So there's a variety of sensors out there that measure moisture. This is a product from the University of Wisconsin using Department of Defense satellites, but there's other NASA satellites that provide similar information. And what you're seeing here is a measurement of the total water in the entire column from the surface to the top of the atmosphere. But because water vapor decreases very rapidly from the surface on up, most of this, what you're seeing here, is just the low-level water vapor. So where you see the reds and oranges is very moist areas. The blues and greens represent dry areas. And sometimes you get these disturbances coming off where this dry air gets wrapped in, and that often will kill off these storms. It creates a tongue of dry air that can erode these clouds and make it hard for them to get organized. Whereas once you get out into this area, you occasionally have some pockets of drier air, but for the most part it's pretty moist. And as it restarts here, you can get a sense of a little bit of rotation here. This is the pocket of moisture that forms Harvey in the Gulf. And you can see there's really not much dry air around that storm. So again, very favorable conditions for Harvey to form. So one question, if you remember that original forecast where they thought maybe it was just going to be a tropical storm or a Category 1 storm, where did the forecast go wrong? I mean, clearly there were warm ocean temperatures, there was plenty of moisture, so that would make you think, well, maybe it was the winds. Maybe the winds were projected to be unfavorable. And that can be really hard to detect. And I'm not going to be showing Harvey here because this animation is for a different storm that's really cool. But this is an animation showing in colors, surface wind speed, and then the white that you see is the strong winds associated with the jet stream in the upper part of the troposphere, the atmosphere. And so this shows you undulations in the jet stream, and every now and then you'll see these tropical storms or hurricanes form that show up as high winds. We have some ways of measuring winds from space. We can measure surface winds using a couple different techniques, but that only really tells us about what's going on at the surface. And what we really want to know is what's going on throughout the atmosphere. Now, the geosynchronous data, if we track clouds, can tell us how those clouds are moving based on the wind, but the wind information is sort of spotty. So here's why I showed this animation, because this is Superstorm Sandy from 2012. And you'll kind of see this hint of a dip in the white here associated with the jet stream, which is what helped pull Sandy back in toward the coast. This was a late season storm in, I think it was October. And so the jet stream tends to be more active and dipping down further south. And it just so happened that as Sandy was moving up, there was a superposition of the two storms that allowed it to move westward instead of the typical pattern of just moving out to the northeast. One of the interesting things about Sandy is that because of that dip in the jet stream, the air got really cold behind the storm, and actually areas in the Appalachians were snowing as a result. So a very weird storm in that sense, very atypical. Now, a lot of these measurements are taken from large spacecraft like this. This is the GPM satellite. We have two different radars on there and the microwave sensors up here. And to scale, you can see this is the size of like a small school bus or something like that. But the trend right now is toward miniaturization. We're trying to get things as small as possible because they tend to be less expensive, they're easier to launch and cheaper to launch. So it allows us, NASA used to have a motto back, I think it was around the time I started in the early 90s of better, faster, cheaper or something like that. Well, this is sort of going in that regard. This is a new radar. You can see it's about the size of somebody's upper body. It's not nearly as advanced as this radar, but it has some decent capability, and it's really cheap. You can fly a whole bunch of those at less capability, but really increase your sampling, so you're just getting observations more rapidly. There's another satellite here called TEMPEST, which is one of these microwave systems. And two of these two were recently launched from the International Space Station by JPL, the Jet Propulsion Laboratory. And they were lucky to get a direct overpass over a storm. I'm trying to remember, I think this was Typhoon Trami in the West Pacific. And so the data that you see, that's sort of like a vertical curtain across the storm, where you see these towers of precipitation here. This is basically mapping out the precipitation. That's from the radar. So it only gives you beneath the satellite, whereas the GPM satellite can scan across the storm. But it gives you useful information. And then the microwave satellite, because of the different channels it has, it can see information at different levels of the atmosphere. So you get these different horizontal slices, and when you combine them, you get a three-dimensional structure of the storm. Maybe not quite as good as GPM, but pretty good for very small and inexpensive satellites. So coming up in a couple years, we have a new mission coming up called TROPICS. I'm involved in this one. And the idea here is to launch these really small satellites that have these microwave sensors. This thing is about this big. I wish I had a model of it. It's about the size of a big loaf of bread. And then it has this big solar array to get its energy. And we're going to fly 6 of these. The advantage is they have multiple channels, so we scan different parts of the atmosphere. some of which will give us information on precipitation. Other combinations of these channels will give us information on the temperature and humidity in the environment of the storm. But because we have 6 of these flying, and we're flying only down in the tropics, we're not worried about the poles, we're really trying to focus on tropical cyclones, we're going to about half of the time, we're going to get observations about every 50 minutes or faster. So very rapid repeat observations compared to what you can really only get from the geostationary satellites right now. But this is a capability that you can't get from geostationary orbit right now. So this is going to be a pretty big advance in terms of describing the more rapid evolution of tropical cyclones. Now, these different satellites have a number of different applications. They can be used in numerical weather prediction. That means getting the data into the forecast models to improve the forecast. They can be used by the forecasters even more qualitatively, where they just say, well, here's what I see in the satellite. What was the forecast telling me before? And do I have evidence that the forecast is actually wrong? What does it tell me about how the storm is evolving and whether it's going to intensify and whatnot? It can be a variety of data can be used by emergency responders, particularly in terms of flood and landslide monitoring. Power industry, you think of Hurricane Maria and how it knocked out power over most of Puerto Rico. So using satellite data, we were able to assess how much of the island was without power and track how quickly it was being restored and in what parts of the island. It can be used for disease monitoring. So when you have flooding, that means, and especially in the tropics, what do you get? Mosquitoes. And mosquitoes carry a variety of diseases. So there are a lot of people who monitor diseases who really want the rainfall data to be able to do that. And then the insurance industry uses it because they want to be able to assess risk, so they know how much to charge somebody who's got a home on the Outer Banks. They want to know what the risk is for that person being flooded or whatnot. And then it also is used by the people who insure the insurers, the reinsurance agencies, because if an insurance company can't afford to pay out, the reinsurance company makes up the difference. So they use a lot of our data. So there's a variety of different applications. So it goes beyond the science to real everyday applications of these data sets. So now I'm going to transition to the aircraft side of things. This is a video from the NOAA P3 showing that their flight into, I'm not even sure what storm it is, but it's an amazing video because it gives you their perspective of what it looks like flying through the storm once they get into it. Hopefully the lights here will still allow you to see it well. So they're flying down at low levels, typically about 1,500 meters or so, which is about 4,500 feet. It's a pretty rocky ride. I cut out some of the parts where you really see them bouncing around because I didn't want the video to be too long. But now you can see the eye wall of the storm there and looking up to the top of the eye. So just an incredible view. Only a small percentage of people get that view. I've been fortunate to have gotten it back in 2010 when we were doing a NASA campaign and did a couple flights into Hurricane Earl as it rapidly intensified. But I didn't have that sort of view out of the cockpit. I had a view that basically was like over the wing, which wasn't ideal. But it's a pretty amazing experience. I've had friends who have done it, who work at NOAA, and some of them only do 1 or 2 flights and then they're done. It all depends on how strong your stomach is, I guess. But this is the key way of collecting data. It was first done back around World War II, and the story goes, and I haven't verified the story, but the story is there were 2 pilots. I can't remember if they were at a bar or something like that, but one dared the other to go fly into a hurricane or typhoon, and he said, sure, what the heck, and started doing it, and they realized they could actually do it. It wasn't always easy, and I don't remember offhand whether they lost some planes during those times, but since we've been doing regular reconnaissance going back to about the first set of flights, maybe in the 50s, the more routine flights from NOAA and the Air Force, probably the 70s, they've never lost an aircraft. They've come very close. In Hurricane Hugo, they almost lost the plane when it hit a really strong small-scale vortex on the inner side of the eye wall, knocked out an engine or 2, and they actually had to circle around in the eye for a while till they got high enough that they can exit, because they didn't want to exit it down low because they were afraid of hitting that same feature and knocking out the rest of the engine. So that was probably one of the scariest moments on the NOAA side. Now for NASA, we do a variety of campaigns. We've been doing them since 1998. And our last one was in 2017. We do these campaigns to calibrate and validate satellite sensors to test out new sensors. Before you ever launch it into space, you want to make sure it works, and the easiest way to do that is to fly it on an airplane. And then we do what we call process studies, trying to understand how a hurricane works. And this video shows a set of flights we did into Hurricane Karl in 2010 as part of this experiment. We had the Global Hawk, an unmanned aircraft flying out of California. There were the Air Force plane already here, a couple NOAA planes come down, and then 3 other NASA planes come in, no, 2 other NASA planes come in, and we had all these aircraft flying into the storm at different levels at the same time. This is hurricane reconnaissance on steroids. We don't normally have this many planes flying. Usually you might have the Air Force and NOAA out there. But when we do our field campaigns, we always coordinate with them, because if you can maximize your observations, you can do a lot more science. And so in this case, most of the planes have gone away. There's a second Air Force C-130 out here, but he's going to be going away pretty soon. Let's see. So those planes have gone off. And then he eventually gets to the point where the only one that's left is the Global Hawk. The Global Hawk can fly for 24 hours, maybe a little bit more. And in this case, even flying from California, it flew over the storm for 14 hours. A typical manned flight is 8 hours, and you may be lucky to get 6 of those within the storm. So the unmanned capability gives you the opportunity to see some things that you might miss by only getting brief looks at the storm. This is one of the aircraft that we use. It's the DC-8. That's the one that we flew into Hurricane Earl with. It flies at around 40,000 feet, so you're avoiding the worst of the turbulence within the storm, and never really had any issues. If somebody remembers at the end, I can relate an experience in which it rained in the aircraft, but I'll save that story for later if there's time. We also have a couple of high altitude aircrafts that fly above the storm. One's an ER-2, which is like a U-2 spy plane, and then a WB-57, which probably is similarly a spy plane, but not quite as high of altitude. This is a visualization showing that the unmanned Global Hawk and one of the radars on it scanning the storm. So what you're seeing here is a measure of precipitation. It's a little hard to make sense of the storm because the radar scans in a cone. It wants to get a look looking forward and looking back as it flies along the sight line or flight line. And the reason it does that is because it's also taking Doppler velocity measurements. And you can, if you look in 2 directions, you can combine those line of sight winds to get the total wind field. So this is one way of mapping out both the winds and precipitation, but it takes a lot of data processing to go from this to something that makes sense. But this gives you a sense of how the storm was sampling, or how the plane was sampling Hurricane Karl with these repeated flight legs over the storm. And with a fair amount of computation, this is what you get. So the colors here represent the intensity of the precipitation. So this is the eye wall in this region where the red is. And then down here is an outer rain band. And then it's a little hard to see here, but all these little black arrows represent the winds that were derived that give you estimates of not only what the maximum wind speeds are within the eye wall, but how that might vary around the storm. And there's even some small scale structures that can't see in this view, but if you really zoomed in on one of these areas, you'd be able to see some of these small scale, even little eddies within the eddies that are really interesting. And we did a study back a few years back where we took this data, the radar data, and we put it into one of the forecast models, and we were able to demonstrate that you not only can improve the intensity forecast, but also the structure forecast of the storm. So collecting this type of data can be extremely valuable. Now, from 2012 to 14, I led a campaign called the Hurricane and Severe Storm Sentinel, where we were using the Global Hawk by itself, but we were actually going to try to use 2 of these. One that would be focused on the environment of the storm, one that would be focused on the inner core processes. Unfortunately, both these aircraft were flight demonstrator models from Northrop Grumman, and so when NASA got them, they were pretty old. And one of the ones we were using was the first one, and it proved to be rather unreliable. So we primarily used the one aircraft, but during those 3 years, we did 670 flight hours of 21 flights, 19, or was it 9 or 19 named storms, 9 named storms. So these are the different storms that we did. This is a view of our control center. There's me. We would look at the computers to look at our flight tracks. The plane is flying around in here, and sometimes you'll see another line changing where on the fly, we're adjusting the storm track based on the motion of the storm. We want to make sure that every time we're passing over the storm, we're hitting the center of the storm, because we're trying to take measurements of the inner core part. So over the course of the flight, we were continually adjusting the flight pattern, working with the pilots to do that. These are some of the instruments. These are Dropsondes. They're little sensors that are released from the plane at the back. You'll see it here in a moment. It'll just fly out, and that'll drop down on a little parachute to measure profiles of temperature, winds, and humidity. Very useful information. In fact, one of the most used data sets from this campaign. Here again, you're seeing the scientists. This is my former grad school advisor. I was able to pull him into this experiment. One of the topics we were really interested in this campaign was how Saharan dust interacts with storms in the Atlantic. All of these African easterly waves that form the seedlings of Atlantic storms usually have what's called the Saharan Air Layer. It's a very hot, dry, dusty air layer to the north of these disturbances. And so the big science debate right now is to what extent that hot, dry, dusty air gets into these storms and perhaps weakens the storms. And so we were trying to do these flights where we map out across the entire storm. This is just showing the clouds in the storm, and the animation didn't show it very well, but we could also measure where the dust was in the storm. This is the nighttime video flying over Hurricane Edward, and right at the very beginning, there was a little darkening in the clouds. That was actually the eye of the storm as we flew over it. This is just showing I can't see it very well here due to the lights, but this is from one of our science team meetings. So every year, everybody on the team would get together. We'd talk about what went right the last campaign, what went wrong, what changes we wanted to make. We talked about the science that we were able to do. So it was always reassessing to figure out what we can do next. NOAA was also partnering with us in this campaign. They provided that Dropsonde system, and in the last year, they provided extra funds for additional flight hours. And as a result of this campaign, NOAA actually did a couple of other campaigns in 2015 and 16 where they used the aircraft, and we helped them out to do this. But their goal was to try to take the observations and get them into the forecast models to see what impact it would have on the forecast models, because their NOAA P3s are getting old. Every now and then they have to put new wings on the plane. They're pretty much at the last time they can do it. So they're looking right now to what's next. What's the next plane we can do? And they wanted to assess the Global Hawk and see whether or not that would be useful for them for their reconnaissance. I think they found that it was very handy. They were seeing some forecast improvements from the data, but it's very costly to run the Global Hawk. We typically only did it for 6 weeks at a time rather than all season. And because these aircraft were so old, they tended to be somewhat unreliable. And unfortunately now NASA has basically decided to retire the aircraft, and we do not have the capability for it anymore. So we're back basically to manned aircraft all the time. Hopefully at some point we'll have additional observations. This is just another example. This flying over Hurricane Edward in 2014. This shows some of the winds and humidity from the Dropsondes, and then this curtain of data shows humidity data from one of the sensors on the plane. The goal here was to map out the environmental conditions, so how dry or humid was it in the environment, and then with the Dropsondes you can see the winds that map out what the wind flow looks like within the storm. And then as it goes around here, if you can see it, there's blue here toward the upper part of these curtains that indicates very dry air aloft to the south. But then as you come around to the north, it's more green, indicating more moist conditions. So the advantage of the Global Hawk is that you're able to sample very large scales. So as you saw in this total flight pattern, we'll go through it one last time, we sampled all around the storm, way out in the environment, and then did all these flights across the storm to sample the inner core. You can't do that with a manned plane. A manned plane coming out here would have just done a few crosses of the storm and gone back. So that was a nice advantage of that aircraft. So what are some of the things that we've learned from these aircraft missions? We've learned about the strength and distribution of strong updrafts or rising motion within the eye wall. This is a good example of radar data from the ER2 showing the intensity of the precipitation. And normally at upper levels you'd see just the yellows and maybe a little bit of orange. But in this case we saw this really dark red. That's a signature almost of a hailstorm within the eye wall of the storm. The pilot flying over this actually didn't want to fly over it again because the ER2 has a very narrow range of speed that it can fly before it stalls, and he was on the verge of stalling flying over this thing. So it proved very difficult to fly over, but that really gave us some clues about what can really occur in these storms. We've learned about some of the mechanisms for storm formation and intensification, better characterization of the structures. As I mentioned before, looking at the Saharan Air Layer and what its impacts are. That's still, I think, a fairly unresolved issue. And then just the impact of these data sets on the forecast models. So with that, I'll stop. This is just a quick summary here that, again, NASA is not an operational agency. We don't do flights for day-to-day forecasting purposes. We're a science agency. So we're trying to take advantage of the vantage point of space to see these storms using advanced research sensors that often prove useful for the operational community. We're always working on new technologies, whether it's technologies for the aircraft or these new small satellites that NOAA is now considering as part of their next generation observing system. And then also using this airborne data to validate the satellite sensors and a variety of other things. So I'll stop there. Hopefully there's still plenty of time for questions, and I'll just leave it here with a map showing our precipitation product for, this was the 2017 hurricane season, just to have that running in the background. So be glad to take any questions at this point. Yeah.
Thank you very much. And you can choose and you'll repeat.
Yeah, go ahead.
Okay, so I moved from East Coast down to Miami, and within months, Hurricane Floyd was coming. I lived in evacuation zone 1, Miami Beach. Did not evacuate, spent the time hiding in the back.
This Floyd in 1999?
Yes.
Okay.
I moved in June, and Floyd came in like August.
September, or the early September. We were at the beach in southern North Carolina and got chased out by the storm.
Fortunately, we never got a drop of rain on Miami
Yep.
Beach, which would have gone under and enough rain. But an urban legend, and I'm wondering if it's an urban legend, was that during Andrew, it sucked live fish up into the hurricane and then deposited them alive inland. Is that an urban legend, or is that actually possible for a live fish to live in a hurricane?
Okay, so the question is, can a hurricane basically suck up fish and then deposit them on land? I frankly don't know. It's not something I normally study. I don't think hurricanes have suction power in that regard the way a tornado would, although you can get, often when a hurricane makes landfall, particularly in those outer rain bands, you can get tornadoes forming. The added friction of land versus ocean helps to pull the air in toward pull it in a way that allows a tornado to form. Now, if you get a water spout, I guess in theory that could potentially pull up some fish and deposit them on land, but that would be more a small scale water spout rather than a hurricane, be my guess.
Is it frequent that you get tornadoes in hurricanes? Because that seems like problems on top of a big problem.
So the question is it frequent to get tornadoes and hurricanes? And for landfalling storms, it's very typical to get them in these outer bands. So whenever you have a storm making landfall, you'll often see tornado warnings. Not so much on the eye wall, on these bands that are further out from the center of the storm, because you get really intense thunderstorms, and there's enough rotation near the surface that getting an updraft on that can really spin up the flow very quickly. So that's not atypical. So, okay.
In the past month, there's been a lot of controversy on the expansion of 5G networks, the impact it will have on weather forecasting, and has NASA looked at that issue and its potential impact on its satellite work?
And so the question is, will the 5G network affect NASA satellites and other satellites? And the answer is yes. We've been looking at this quite a bit recently. The GPM mission that I'm the project scientist on is one of the missions that will be affected. So I mentioned those microwave measurements that we take. Well, one of the channels that we have is right on the cusp of the band that they're auctioning off, and there's enough spread out of that band that it will affect those measurements. And these measurements are primarily related to the sensing of water vapor in the atmosphere, and it affects several of our satellites. It affects several of the NOAA satellites, Department of Defense satellites. I had a plot further back. Let me see if I can get back to it easily.
This is a global issue.
it remains to be seen how bad the interference will be. So I didn't talk about this plot. This represents different observations from different sensors. This shows the forecast impact. So if it's positive, it's a degradation of a forecast. If it's negative, it's an improvement of the forecast. And you see some sensors just give you a little bit of improvement. Others give you a lot. GPM is right up here. And it turns out that half of that skill or improvement from assimilating the microwave imager data comes from that channel. And so we lose half of our improvement ability. And if they start selling off other bandwidth, it can affect other observations. So this is a big concern. NOAA and NASA have been making the argument to the FCC about whether or not, what degree of problem this is going to cause, but we don't know. The U.S. probably would be a significant issue because you just won't be able to get the observations there. Europe they're taking a little bit more careful view of it. From what I've seen, they're going to limit the power that people can transmit in that bandwidth. That would hopefully minimize interference. I think the power limit currently being considered by the U.S. is an order or two magnitude bigger and would definitely be a problem. To what extent it affects things over the oceans, I don't know. Whether planes and ships are using 5G, that can cause interference. So it's still a bit of an unknown. So for a lot of what we've been doing in our assessments, we've kind of assumed the worst case approach where we just lose that channel. But the true answer is it's probably somewhere in between, but we just haven't had time to fully assess it. Other questions? Yeah.
Two questions. One, what happens to the Dropsondes after they are released? Do they decompose or do they just sink into the ocean due to depletion? And related to that, is there any evidence that the smaller satellites are better for satellite contamination around the atmosphere?
Okay, so the first question is what happens to the Dropsondes when they hit the ocean? A good fraction of it degrades and goes away, but some of the electrical components don't. And so when we got approval in terms of an environmental impact, you have to assess the degradation of the ocean by a relatively small number of these things that go out compared to all the other stuff that ends up in the ocean versus the impact this has on the forecast that could save lives. So it's sort of the cost benefit that you look at, and overall, when you consider everything that's ending up in the oceans, this is a minute bit of what's there. The second question, in terms of the smaller satellites, so are you talking about in terms of what's left in space? So the nice thing is that most of these small sats don't have propulsion. So once you launch them, they're continually falling back to the Earth, and they only live as long as they fall back to the Earth, and then they burn up upon re-entry, so they never get back into the Earth's atmosphere. A big satellite like GPM won't completely burn up. It has a big fuel tank that won't. We had a predecessor mission called the Tropical Rainfall Measuring Mission that went from 1997 to 2015 that did what was called an uncontrolled re-entry because the benefit was that it saved more lives than the risk associated with it potentially hitting land if some parts survived. GPM, being a bigger satellite, actually has to do a controlled re-entry. So they save enough fuel that at the end of the mission, they bring it down in a way that they can direct the satellite, what's left of it, into the ocean. Now, it turned out for TRIM, it landed in the middle of the Indian Ocean. It was not an issue. The small sats will completely burn up. I think there is a rule that, if you launch it really high, it takes a long time to fall down. But there's a rule, I think, that limits how long they can be up to like maybe 20, 25 years. So even those eventually they can't be high enough that they won't fall back down within that time span. Yes.
Are you learning anything from your terrestrial programs and from NASA's observations on other solar system planets? Are you able to take information back and forth and improve studies or information either way? And then
Are you talking about in terms of planetary science and what's going on in other planets' atmospheres?
Yeah.
I mean,
back to Earth, back and
to a limited extent. A lot of it depends on, so the question is, to what extent does this information apply to, say, other planetary atmospheres? And that depends on the makeup of the composition of those atmospheres and what drives their dynamics. Here on Earth, because of our atmosphere and the temperature range that we have, we get these sort of disturbances. We have clouds and there are other planets and other systems that have clouds, maybe not water vapor, but something else. And then it would depend on to what extent they had the right atmospheric conditions in terms of temperature. I don't know to what extent some of, like these concepts about, say, vortices within planetary atmospheres, at some level, all vortices follow the same dynamics. It's just that what drives these vortices are the cloud dynamics. But on another planet, that you might have a planet where even without clouds, there may be a certain temperature conditions that still spin up vortices that can be long-lived, or they may have clouds composed of something else. I don't know to what extent that's really being examined within NASA or elsewhere, but it wouldn't surprise me. I know people are looking, obviously, at vortices on other planets, but to what extent they try to connect what we're viewing here in the context of hurricanes, I don't know. Yes?
You mentioned Superstorm Sandy earlier, and you mentioned something about a superposition. Does that explain why, for example, the European model had it right, hitting New York, New Jersey, and we had it wrong, going out to the Atlantic? And is this new software package that they were, I guess, installing today, according to the New York Times, the Global Forecasting System?
Yeah.
Would that help that kind of thing? And while I'm at it, let me also ask about channels. Is that like...
Let me come back to that then, because I'll forget part of the question. So the first question was with Superstorm Sandy and about the differences in the forecasting models between the European Center and the U.S. models. And very early on, I mean, we're talking, I think it was 7 days out, 5 to 7 days out, the U.S. model had the storm going out into the Atlantic, whereas the European model was first to pick up on this movement back toward the coast. And that was because their model was handling that superposition of the jet stream with the storm better. And it just caught the phasing better, so that the timing was such that it would pull the storm toward the coast. My guess would be that the U.S. model maybe was moving that trough at upper levels too fast, so that it would interact with the storm in a different way that would just push it out to the east. So NOAA this week is releasing their latest generation model. It's replacing the old one that was involved in those forecasts. The idea with this development is that it was a whole new dynamic core, the way that the equations of motion for the atmosphere are cast into computer code is different. Different types of physical parameterizations and such. So in theory, it should be better. And I think for a lot of what they've been looking at for most weather, they found that it was doing better. I think there was a bit of a delay due to hurricanes and whether it was doing hurricanes as well as the current model. And so that they wanted to look at that a little bit more. But my understanding is the whole point of releasing it is that it shows better skill than the older model did. Otherwise, they wouldn't move to the new model. So what was your second question?
Thank you for that, and thanks for coming. This is great stuff.
Sure.
We're lucky to hear you. You showed that cool chart of surface temperature on the water, and it gets warmer closer to basically Houston. Does that matter? If a hurricane wants to be a big hurricane, does it want differences in surface water temperature, or is even better? And then one last quick one, channels. You mentioned that a couple times. Is that like what is that? Is that a wavelength, like what a spectrometer would read, or something else?
Yeah, so the first thing about the ocean temperatures and whether the storm wants just a broad, more uniform area of hot water, or do variations matter in terms of will it intensify better with certain variations? And the main thing you want is just the warmest possible water, and the way that most of the storm will feel that warm water is if it's uniformly warm. So in an area like this where it's just a narrow ribbon of very hot water, it'll only go through that really rapid intensification when it's passing over that ribbon. In the Gulf of Mexico, there's actually a feature called the loop current, which gives you this really warm eddy. So it's a small circular area of warm waters, and that often leads to or coincides with when storms rapidly intensify when they move over that, assuming all other conditions are favorable. You may also get areas where there's a pocket of colder water, which would then be unfavorable. In this case, it was more right along the coast, so you would expect the greatest intensification to be right as it's approaching the coast, as long as those shallow coastal waters don't quickly mix up colder waters, which may have happened as well. So there's a variety of different things going on there, but a storm basically just wants as much warm water as it can get access to. And in terms of the channels on a satellite, yeah, that just means that you're measuring the microwave energy at different areas in the spectrum of radiation. So there's certain frequencies that are optimal for measuring water vapor. So this whole issue about the 5G, it's because they're selling off bandwidth at a certain frequency. That's where we measure water vapor. There's other parts of that spectrum where we measure temperature, others where we do better with precipitation. So a number of things like that. So we have different channels to measure different aspects of the atmosphere typically.
Okay.
All right. Yeah, one more.
I'm interested in the aircraft patterns and how you get there. And by the way, you might want to add the Beach Boys to the one where the guy's bobbing around. It looks like but unlike FBI grids, you know, where they're looking for a body or a person or whatever, it looks like there's an initial back and forth, and then it goes diagonal. I was just curious, how long was that time frame? Because not only you're trying to cover everything, but presumably the storm is moving.
Yeah.
So it's like,
So
it's a complicated
yeah.
problem.
So the question is basically about how you do your flight planning, and I think the particular rationale for why the flight pattern that we're using. And so the thing you want to do most is get the information at the center of the storm. But ideally for hurricane science, you want to do a cross from outside the center across the center and get that radial structure. That gives us, you know, if you think back to this schematic of the storm, so we want to see as much of that structure as possible. And to the extent that there's not a lot of variation around the center, all it takes is one slice through and we get a decent sense of the structure. And so we design the flight pattern so that we cross the storm. But we like, because we know that it's not really uniform around the center, we'll then, once we finish that leg, we'll go to another one, come in along a different radial, and we'll do that as many times as possible. The length of the legs, you do enough that you certainly catch the eye wall and maybe some of the outer, inner or outer rain bands, but you don't want to take too long because you're only out there for 3 to 6 hours. So, and each of these legs may take half an hour, and if it's really long, it may take 45 minutes, and then it takes time to then set up for the next leg. So a lot of times you may just keep it really tight and just do a bunch of crossings to see how the intensity is varying with time. But it's not that hard actually to follow the storm. They're moving relatively slow, maybe 15 knots. And so you can readily design your flight pattern. If you assume a storm motion, we have code that you put in the pattern you want, and the code will account for the storm motion and spread it out so that it's basically following the storm motion. So, and then what you do from that is then you just make smaller adjustments to stay with the storm.
Maybe
Right.
the last question could be mine.
Okay.
I wanted to know a little bit more about that Saharan dust and how that works, and I'm in favor of it if it stops the hurricanes.
Yeah, you think about the Saharan dust in terms of the ingredients you want for a strong storm. You want moist air, weak wind shear. I didn't say much about temperature, but you want a temperature profile that's conducive for thunderstorms. And the problem with that hot, dry, dusty air, you already heard one part, dry. The hot part is that the hot air overlies colder air over the ocean, and hot air over cold air means a very stable condition that when the air tries to rise up, it very quickly finds itself colder than its environment, and so it wants to sink again. And so it's very hard to get any deep clouds forming. At the southern boundary of that Saharan air layer, because you got hot air to the north, colder air to the south, you've got a temperature gradient, and a temperature gradient is what drives winds. And so you end up with a low-level jet, easterly jet, that can potentially increase the wind shear around the storm. Now that's still debatable because that jet also, because the winds change rapidly from the core of the jet to the south, it actually can contribute to rotation as well. And so I've done some work that kind of, for a while, everybody just said, oh, the Saharan Air Layer is always a negative influence. It's always suppressing storm activity. And I said, well, wait a minute, because a lot of the evidence people were using was somewhat circumstantial. And I said, well, just because the storm weakened, there could have been other things causing it to weaken. In fact, I can find plenty of cases where storms rapidly intensified despite the Saharan Air Layer right around it. And so I at least called into question whether that's the answer. The dust can interact with the clouds and precipitation because they can form the seedlings for droplets. So a lot of cloud droplets form on aerosols of some sort. It might be dust, it might be smoke or something else. But what happens is that the more particles you have, the more that water gets spread out over a larger number of smaller drops, which makes it harder to form rain because rain forms from collisions, but collisions are less likely if they're tiny drops. And so some people think it delays rainfall formation until the updraft gets higher, and then suddenly it invigorates the convection at upper levels. That's still very debatable as well. So at this point, I think there's a lot of ideas out there. Some people have actually shown it can favor storm development. Others show it suppresses them. And I think we need to get our computer models sophisticated enough and our approaches sophisticated enough to get a final answer on it. So for me, it's still up in the air as to what its true role is. We do know in general that the dustier a season is, the fewer hurricanes you get, but it may not be an interaction that's on the storm by storm level, but maybe in terms of the larger scale patterns that it sets up. It may cool the oceans because it blocks some of the sunlight. It may create more unfavorable wind conditions. So it may just be that the broad scale conditions are less favorable rather than the small particles themselves affecting the cloud droplets and rain and whatnot. So, all right.
Thank you very much.
Oh, actually, there's one.
Want one more?
Well, we got a couple of young audience members who want to ask questions. If we can do them real quick. Yes? Oh, the rain in the plain does not fall mainly in Spain. So I mentioned earlier that it once rained in the plain. And so when we did in the DC-8, it's an old passenger plane, we were flying from St. Croix into Hurricane Earl during its earlier stages. And as we were getting ready to move onto the runway, we took a bird in the engine. They inspected the engine, washed it off. There wasn't much left of the bird, unfortunately. And once they decided that the engine was fine, we were given permission to go. The problem was that whole time we were sitting there while they were doing this, we had all the doors open. And St. Croix, if you've ever been down there, is very moist and tropical. And so we had all this moisture in the plane. So now we take off, we go up to 40,000 feet. It's pretty cold up there. And by conduction, the inside of the plane starts cooling off. And so it formed a lot of ice on the inside of the plane, but not where we can see it. There were still some compartments. There's not quite like a passenger plane, which I suspect this happens in passenger planes all the time, but they have ways of getting rid of the water. But it's a modified plane, so there's some areas where you can't see what's going on, and there was a lot of ice up there. And toward the end of the flight, we decided to go down low to fly into the Saharan Air Layer. And once we got warm enough, all that ice melted, and all of a sudden it started raining in the plane, and we were scrambling. We had fancy equipment, electronic equipment on the plane, so we're trying to cover everything, shut things down, so that we don't fry any components or anything like that. So that was a very rare experience to get that, and it was a pretty good shower, I should say. So anyway, that's it. Thank you for coming.